Okay, let's start. It's a great pleasure to have Professor Victor Ostrik from Oregon University and to give the quantum symmetry seminar talk today. Victor is a leading expert in the theory of fusion categories and representation theory in general, and he has done a very influential work, and we are still quoting and using today. So yeah, he will talk about his recent research on growth in tensor powers. Victor, please.
Okay, thank you very much, Ivan. So I'm going to give a talk about, well, hopefully very elementary talk about, there will be almost nothing quantum in my talk, so kind of my categories are going to be symmetric tensor categories, but hopefully interesting. So it's based on a joint work with Kevin Coulembier, Pavel Etingof, and Daniel Tubbenhauer. So most of this talk is going to be about our joint paper with Coulembier and Tubbenhauer, but maybe in the end I will mention some extra developments with Coulembier and Etingof. So let me start my talk. So here is setup. So you start with any group you like, absolutely any group, and any field you like. Again, absolutely no restrictions on a field. And you take some finite dimensional representation of group over this field. And well, there is a way to build new representations out of this, namely taking tensor powers. And now goal of what I want to talk about is just to say something, well, something non-trivial about decomposition of these tensor powers into indecomposable summands. So in general, it's kind of hopeless problem. So I mean, it's kind of way too general. So I want any group, any field, any representation. And, I mean, to give you a lot of details would be impossible. But it turns out that I can say you something interesting. So asymptotically, so when this number n is large, and which applies kind of in this very general situation. So let us kind of, I'm going to define very important sequence for me. So I'm going to take this tensor powers, and each tensor power, I will decompose it into indecomposable summands. And I will just count number of the summands. So how many of them are there? So if some summand appears 5 times, I'm going to count it 5 times. So I count them with multiplicities. And well, I want to understand something about this sequence. So I have this sequence Bn, so just number of indecomposable summands in tensor power of V. Well, so for example, how it behaves when n is very large. So kind of what I can expect from this sequence. So let us do some examples first. So I will state my theorem somewhere, well, in the middle of this talk. But let us look at some examples where I can say something which is clear. So first example, so let us assume that my group is finite and my field is field of complex numbers. So in this case, everything about representations of finite groups over complex numbers is covered by classical character theory. So every representation has a character. And so on. So what is important for me is that any representation in this setup is completely reducible. It's direct sum of irreducible ones, and there are just finitely many irreducible characters. That's kind of classical facts. Well, let M be maximal possible degree of irreducible characters. There are just finitely many of them, so there is maximal possible. And something that's kind of almost trivial. So I have this inequality here. So this number Bn, it's certainly less or equal than dimension of my V power n, just because dimension of my tensor power is exactly this dimension of V power n, and each indecomposable summand that contributes at least one dimension to total dimension. So that's kind of obvious. But on the other hand, any indecomposable summand is not going to contribute more than m, this kind of capital number m, to total dimension. So my number Bn, it's somewhere between dimension of V power n and dimension of V power n multiplied by some constant, by 1 over m. So asymptotically, it kind of behaves like a geometric progression with denominator dimension of v. So that's kind of our first lesson here. So I want to give very easy example to show that things are kind of well, maybe not as good as one can hope. So for example, if you take for gamma dihedral group of order 8, and for v it's two-dimensional irreducible representation, so tensor square of this two-dimensional representation is going to be sum of 4 one-dimensional representations. And from this, it's kind of very easy to deduce that this sequence Bn is going to be 2 power n when n is even. So basically, all summands are going to be one-dimensional. Or 1/2 of 2 power n if n is odd. Just because all summands are going to be copies of this two-dimensional representation. So that's kind of easy computation. But this shows that in general, I do not expect that my Bn behaves like some constant multiplied by dimension v power n. So, I mean, so in this example, this constant it kind of oscillates between 1 and 1/2, and kind of, and there is nothing you can do about it. So this is just not true. Even the simplest example. So let us do one more example. So now my group gamma is still finite, and I'm going to take some field of characteristic P. So I want to consider situation when representation theory is not semi-simple anymore. So things are getting kind of more complicated, and well, hopefully I will learn something from this. So, well, modular representation theory, it tells us that, well, you still have finitely many irreducible representations, but also you have finitely many indecomposable projective representations. So usually they're called PIMs, so projective indecomposable modules. So let us introduce number m, which is maximal dimension of such projective indecomposable. M is minimal dimension. And there is a theorem, which is now non-trivial theorem, interesting theorem, which says the following. So assume that you have, assume that my initial representation is faithful. Then some tensor power of this representation is going to contain some projective summand. So sooner or later, you are going to see some projective summand in decomposition. Okay, now corollary. Corollary is that there is a very nice property of projective modules under tensor product. If you take any representation and tensor it with projective one, you're going to get projective. And just by using this and this theorem of Brian Kovacs, you can deduce that there is some constant such that total dimension of all projective summands that you see in V tensor n is going to be greater than some constant multiplied by dimension of V power n. It's true for all sufficiently big n. So for some small values of n, you might have no projective summands at all. But starting from this point, which is guaranteed by Brian Kovacs, you will have estimate like this. So basically, well, I will have enough projective summands to cover dimension of V power n part of total dimension up to some constant, which is some positive number. So, well, in particular, it gives me an equality like this, that total number of summands is still less or equal than dimension of V power n, by the same reason as before. Every summand contributes at least one dimension, but it's greater than some constant multiplied by dimension of V power n. Well, maybe I should say that this is, again, it's true. Actually, no, it's true for any n. If you choose this constant C prime in correct way, it will be true for any n. So kind of my Bn is still between kind of two copies of dimension of V power n multiplied by some constants. So and these constants can be actually computed out of this m capital and m small. So again, we see this this kind of behavior. And maybe interesting thing here that kind of when you look at this big tensor powers, most of the summands are going to be projective summands, and actually only tiny part is going to be non-projective. So that's maybe interesting thing here. So let me say what to do if so this Brian Kovac theorem, it applies only on the assumption that V is faithful. What to do if V is not faithful? Well, if V is not faithful, then it factors through some quotient of group gamma. And then, well, then it's going to be a representation of this quotient, which is faithful. And this theorem is applicable. And basically, my corollary is still true. So my corollary still holds, but you have to apply kind of all my previous arguments, not for group gamma itself, but for its image in my representation. Example number 3. Let us take for my field a field of complex numbers, and let us take for my group gamma. So now my group gamma is going to be algebraic group SL2. But kind of all my theory applies anyways. Let us take most obvious representation of SL2. So SL2 by definition acts on two-dimensional space on C2. So let me denote it by V. Well, let us take tensor powers of this V, and let us just count this number of summands that you're going to have. This is really easy exercise in characters for SL2. And you will see that this sequence Bn is given exactly by middle binomial coefficient. So take binomial coefficient with, of n. And well, if n is even, it's exactly in the middle. If n is odd, it's kind of as close to the middle as possible. So that's number that you're going to get. Using Stirling formula for factorials, you can see that asymptotically this sequence Bn grows like this. So you have 2 power n, and you should divide it by square root of pi multiplied by n. And I might be wrong by factor of 2. I mean, maybe some number 2 should, maybe it should be 2 pi and not pi. So I don't remember right now. So, but anyway, so what I want to emphasize here is that things are kind of different from our finite group setup before. So now Bn is not 2 power n up to some constant. So it's not bounded by 2 power n times one constant, 2 power n times some other constant. You have this square root of n in denominator. So it grows kind of in a little bit slower way than 2 power n. So that's kind of what we can observe from this example. Well, you can play the same game with three-dimensional representation of SL2. Well, again, you can write down what is character of three-dimensional representation is. So, well, in suitable normalization is going to be q plus 1 plus q inverse. Then character of tensor power is going to be q plus 1 plus q inverse power n. And this sequence Bn for this three-dimensional reducible representation is going to be exactly free term of this Laurent polynomial. So kind of you compute this big power and you compute coefficient of 1. So kind of, and that's exactly total number of representations. Just because all representations that you are going to see, they are going to have one-dimensional zero-weight space, and basically, well, you just need to compute total dimension of zero-weight space. So this example shows that in general, I do not even hope for nice formula for this Bn. So this formula with free term is best I can do. I mean, you can maybe rewrite it as some sum of some binomial coefficients or something like this, but you cannot write some nice final formula like, you know, one binomial coefficient or something like this. So it's kind of really hopeless to find this sequence Bn even in a relatively simple example. So that's kind of one example of this. But asymptotically it behaves nicely. So it's 3 power n divided by square root of n up to some constant. This constant is computable. Let me not, and it has something to do with square root of pi, but well, I don't remember this constant right now. So, okay. So let me state our first result. Oops. So theorem number 1 is that what we observe is kind of general behavior in characteristic 0. So if you happen to be in characteristic 0, and if it so happens that this sequence Bn is greater than dimension of v power n multiplied by some constant, so this is not applicable to my SL2 examples because you have the square root of n in denominator. Then there are very few groups which would work in this setup. Namely, well, precise statement is that the risky closure of the image of gamma in group GOV is a finite group extended by a torus. So maybe let me say something equivalent. So equivalently, gamma contains subgroup of finite index such that gamma 0 consists of simultaneously diagonalizable matrices. So basically of diagonalizable matrices with respect to some particular basis, which I don't know in advance, of simultaneously diagonalizable matrices. So, I mean, maybe one way to think about this. So this in particular, this subgroup is just abelian. So essentially, my group is very close to the finite group. So kind of the only thing that might happen that in addition to finite group, you have this kind of extra diagonalizable subgroup. So that's one result of this type. So basically, in characteristic 0, if my group is kind of is not too close to finite group, you have to divide by some by square root of n or something like this. So kind of my sequence cannot grow too fast. Okay. One more example to show that things are getting really complicated after a while. So let us play the same game, but in positive characteristics. So let us take a group SL2, just as before. But my field now is field of characteristic 2. And let us take again some natural representation of SL2. Let us take its tensor power. So representation theory of SL2 in positive characteristic is not semi-simple anymore. So there are kind of complicated representations which appear. Well, there is a conjecture which, well, most interesting part of this conjecture is due to Etingof. And conjecture says that in this case, this sequence Bn behaves like this. So you have 2 power n, you divide it by some power of n power alpha, n multiplied by some constant. And maybe most interesting part of this conjecture is precise value of this alpha. And this precise value is something like 1/2 log modulo 2 of 8 divided by 3. Well, so maybe before Etingof conjecture was that there is some alpha for which it's going to work, and somehow Etingof, well, based on numerical experiments, you can kind of find approximate values of this alpha. And now, if you are smart enough, by looking at this approximate number, you can make a guess that it might be something like this. So that's actually maybe interesting thing here. Okay, any questions about the examples? So maybe let me advertise this conjecture by Etingof. It's kind of it's completely conjecture in the realm of combinatorics. So this Bn, there is a recursive process of computing this Bn. It's not something that is difficult. I mean, you can compute it on computer, so it's not really something mysterious. But kind of question is, you have this sequence, and you need to kind of find out how it behaves asymptotically. That's all. But it seems to be quite difficult. So this so it's not quite recurrence relation, but slightly more complicated than this. And well, because of this, it makes it difficult. Okay, so this is essentially just beginning of the story about SL2 in positive characteristic. You can ask, the same question about other representations of SL2 in positive characteristic, even in characteristic 2. So take for V not two-dimensional, but some other representation of SL2. For example, maybe for all of them, you will have similar behavior. So dimension of V power n divided by n power alpha. Well, maybe this alpha is going to be absolutely the same for all representations. That's my hope, at least. At least this is what I see in over complex numbers. So for complex numbers, my Bn is always dimension of V power n divided by square root of n, and this is multiplied by some constant. So asymptotically it behaves like this. So for in characteristic 0, this constant alpha equals to 1/2. So because you have this square root of n. And in characteristic P, well, some other power, and we don't even know that it's going to be the same power for all possible representations. Maybe yes.
Explanation for the 3. 8 divided
3. So this is just 2 plus 1. So number 3. So okay. In characteristic 2, you will have some similar formula which would involve. I think in characteristic P, you'll have something like 1/2 log with base P, something like 2p squared divided by P plus 1. So number 3 appears just because it is P plus 1. It's not, I mean.
That looks better.
But this might be, I mean, this is just a guess. So, I mean.
Yeah.
Okay. Let's move on. So general case. So again, we have absolutely any group gamma, any field F, any representation V. And well, I will try to measure how fast my sequence Bn grows. And standard calculus way to measure rate of growth of a sequence is take nth root of the sequence and take limit as n goes to infinity. Well, in calculus, you usually take a upper limit, sublim of the sequence, because kind of you are not guaranteed that this limit exists. But actually, in this setup, this limit really exists. And this is because the sequence Bn, it has a kind of convexity property. So if you take Bn plus m, it's going to be greater or equal than Bn times Bm. So basically what I'm saying is that if you take n plus m's tensor power of V, then you can write it as V tensor power n times V tensor power m, and kind of total number of summands that you are going to see. Well, you can get at least every summand from V tensor power n multiplied by every summand from V tensor power m, and you'll get at least this many summands as Bn times Bm, and maybe you have even more than this. And this convexity property, it guarantees convergence of this sequence by something that is called Fekette's lemma. So this is some lemma from analysis. And well, here is our main theorem, which may be not so surprising out of after all my examples, that this number beta of V is always the same as dimension of V. So maybe what is great about this theorem that it's kind of it's very, very general. It applies kind of well for any group, any field, any representation, and so on. So that's why we're happy about this. And actually, it applies even slightly more generally. So we can take for gamma not necessarily a group. You can take semi-group, and the same is still true. You can take supergroup, so you can well try to play the same game where my group is maybe an algebraic group, but it's supergroup, or maybe a super Lie algebra, and you consider representations which are super vector spaces, and well, you have absolutely the same theorem. So this dimension here is actual dimension, not super dimension. So actual dimension of super vector space. So dimension of even part plus dimension of odd part, so not minus. It applies for some abstract categories like Tanakian categories. So this is interesting if my base field is not. So if you have Tanakian category of algebraically closed field, it's essentially a representation category of some algebraic group, and you can apply previous theorem. But it applies for Tannakian categories even for algebraically, for fields which are not algebraically closed, and then it's kind of a little bit more interesting. So in this case, it's related with representations of some groups, but by some non-trivial constructions and so on. So let me say very few words about proof of this theorem. So maybe I kind of advertise how general it is, but essentially it follows from one special case. Namely, we can take for group gamma algebraic group GLV, and for representation V, well, GLV acts on V in natural way. And if you can prove a theorem in this setup, you can prove it in general. So if you have any other group gamma, so if if you have something like gamma prime inside of GLV, well, you take this V tensor power n, you can first decompose it as a representation of this GLV. And my theorem basically says that you have sufficiently many summands if you decompose it as representation of GLV. At least dimension of V power n summands, well, up to some factors which do not contribute to this limit of nth root. But this means that for gamma prime, well, for gamma prime you can have only even more direct summands, just because every GLV summand, well, maybe it decomposes into some summands for gamma prime, maybe not, but at least number of summands is not going to decrease, it's going only to increase. So if you can prove it for GLV, you are done kind of in general. So that's first trick. And now for when my group gamma is GLV, this representation V is something that is called a tilting module for GLV. So a series of such tilting modules was developed by Stephen Donkin, and in kind of one great property of tilting modules is that tensor product of tilting modules is again tilting module. So in particular, tensor power is going to be tilting module. It decomposes into tilting modules. And another great property is that we have kind of complete classification of tilting modules. We know how they behave. I mean, there is exactly one tilting module for every particular highest weight. So they're kind of classified by highest weight theory. So what we don't have is there is no nice formulas for dimensions of tilting modules. So I know that there is one tilting module for each particular highest weight, but there is no nice formulas for dimensions. And actually, it's kind of one of the big questions in the theory of algebraic groups. So there are some conjectures due to Lustig, Jordi Williamson, and other people, what to expect in general. But these are just conjectures. But luckily for us, we were able to deduce this kind of gross estimate from known information about tilting modules. So kind of you don't need to know exactly all of their dimensions. You just need to know some information about sufficiently many of them. Okay, so this is our theorem. So this is kind of maybe my very brief remarks about proof. So here is kind of maybe one question which remains and which will make this theory kind of much more subtle and much more interesting. So maybe this sequence Bn behaves again as dimension of V power n divided by some power of n. Maybe this power depends on my representation or my group or something like this. So maybe there are some constants which kind of bound my Bn between this kind of multiples of this sequence dimension of V power n divided by n power alpha. So I don't know whether it's true or maybe not true. Maybe easy thing to prove that this is true in characteristic 0. So if characteristic of my field equals to 0, this is actually not too difficult to prove. But if you're in positive characteristic, well, even for SL2, it's difficult. So we don't know how to prove it. So this alpha would be some kind of next term in our asymptotics, and it sounds like it's extremely interesting term in our asymptotics. And at this moment, it's very difficult to say what this alpha is. So maybe that's first part of my talk, where I try to describe this kind of general growth for representations of groups, and kind of when you count number of indecomposable summands. So maybe main message which I want to send is that there are many open questions which seems to be very elementary but very difficult. So that's or maybe they're not very difficult but very interesting at least. Okay, so now I want to describe some variations of what I was talking about. You can count this indecomposable summands in some other ways, and it's actually turns out to be interesting and kind of well, some interesting things appear and so on. So okay, so there are several versions, and let me try to describe all of them. So or at least some of them which I know about, and in principle you can try to come up with your own version of this. So example number one. So you have a finite group. You study what happens in characteristic P, positive characteristic. Well, we discussed before that most of the summands that we are going to see are going to be projective summands. So and well, they kind of contribute me a majority of indecomposable summands. So you can ask, what about all the other summands? So what can we say about this? And this is exactly what was defined by and studied by Dave Benson and Simmons. So well, so let us define a new sequence, Cn of V, and it's number of all non-projective summands that you are going to see in this tensor power. So we just ignore projective summands. We know that they are majority. We're kind of interested in remaining guys. And let us play the same game. Let us define gamma of V as limit as n goes to infinity of nth root of this Cn. So this limit again exists, so it's kind of very similar arguments as before. And this is some invariant of representation of finite group. So this gamma of V, it's some real number, which is some invariant. Benson and Simmons proved number of very interesting properties of this invariant. They computed it in some cases. So maybe, well, I don't want, well, maybe I'm not ready to tell all properties of this. So most of the time it's strictly less than dimension of V. Well, in some degenerate cases, so for example, when characteristic P does not divide order of the group, so when essentially you are doing characteristic zero computation, it equals to dimension of the group. But most of the time it's not. Most of the time, well, very often this number is not integer at all. It's just some number. So in all examples known, this number is algebraic number, and it's a conjecture that it's always algebraic number, but it sounds like very difficult conjecture. No one knows how to prove. Now, this invariant has some maybe not pleasant properties. It's not additive. So if you take a gamma of a direct sum of two representations, in general, it's not sum of values of this invariant. And it's also not multiplicative. If you apply it to tensor product, in general, it's not product of gammas. So it's kind of, to compute this invariant, you have to think about all representations. You cannot reduce yourself even to indecomposable ones. It's kind of, even direct sums, they do not, I mean, the behavior of direct sum is not reduced to behavior of the summand. So that's sums that makes it kind of difficult. So, well, let me stop here to talk about this invariant. Let me discuss another invariant. So now gamma and F are arbitrary again. And I'm going to count so-called non-negligible summands in tensor power V of n. So again, I don't want to count all of them because we know what happens asymptotically. So let us count most interesting of them. So now most interesting for me are non-negligible. So this means that a dimension of my indecomposable summand is not zero in my field F. So, well, it might be not interesting in characteristic zero, but I will say about characteristic zero in a second. but this dimension happens to be 0 all the time modulo p. So if you study something characteristic p, dimension might be 0 modulo p very easily, and this happens all the time. And in this case, we say that our representation is negligible, and I want to discount them. So I don't want to count negligible representations at all. So maybe one possible motivation is that these projective representations we were talking about for finite groups, they're always negligible. Well, always in modular setup when P divides order of the group. When C of subgroup is non-trivial. So in this way, I'm going to throw away all projective summands, but maybe other summands as well. And this makes sense even if you have no projective representations at all. So it makes sense for general groups, not just for finite groups. And well, now you can play the same game. So you can take delta of V, same limit as before. So this number was defined by Coulembier, Etingof, and myself. Well, this number is kind of similar to what we've seen in this Benson-Simons story, but it's kind of behaves nicer. So in particular, it's additive. So when you apply it to direct sum, you are going to get sum of values. When you apply it to tensor product, you're going to get product of values. So it gives you a character of split Grothendieck ring of all representations. You can also prove that it takes values in algebraic numbers, and even better than this, it's just algebraic numbers which are cyclotomic. So you just have to add primitive root of degree p of 1 to integers and kind of take all possible combinations of integers with coefficients which are given by powers of this primitive root of. So maybe I should write here. It's really polynomials in this primitive root of unity. You don't need to do any divisions or anything like this. So, it's sums that behaves nicely, something that takes values in some reasonable ring. So maybe one example of this is that if you take for gamma group Z mod 5, so cyclic group of order 5, and if you take for F field of characteristic 5, well, not surprisingly, because I want to see some modular behavior, and if you take for V, so this group gamma, it has only one irreducible representation, but it has 5 indecomposable representations. So you can take two-dimensional indecomposable representations. There is only one. Then this delta of V is going to be exactly golden ratio, 1 plus square root of 5 divided by 2. And this number is can be expressed in terms of root of unity of degree 5. So that's kind of takes well, it's connected with what I said before. And maybe great thing about this theory about this particular invariant that you need theory of symmetric tensor categories for this. So the only known proof uses some non-trivial results about symmetric tensor categories in positive characteristic. Need theory of symmetric tensor categories. Well, in characteristic E greater than 0. And in particular, you need you need to know that under some assumptions, if you have such a category, it has fiber functor to so-called Verlinde category, and so on. So that's quite non-trivial thing. And well, finally, let me discuss one more variation of things which we are talking about. So again, I'm going to play the same game. I'm going to take some representation. Sorry. Let me go back for this non-negligible example. So it's, as we discussed, it's not very interesting for characteristic 0, because dimension is, I mean, it's some positive number, it's never 0. But actually it becomes interesting if you allow yourself to consider not groups, but supergroups, so or superly algebras and so on. So in this case, dimensions might be negative, might be 0, and in this case, it's kind of quite interesting result. Well, so maybe use super groups in characteristic 0. And one more thing. So I'm going to play again absolutely the same game as before, but I'm going to do it differently now. So now I'm not going to count indecomposable summands anymore. So I want to count just number of irreducible subquotients in Jordan-Gölder series. So take this V tensor power n, find Jordan-Gölder series and try to find, find lengths of Jordan-Gölder series or kind of lengths of my object as object of abelian category. And now let us play the same game. Let us define, well, one more invariant. So now it's a limit as n goes to infinity of this new sequence an. And what is great about this number is that it makes sense in any tensor category. So if you have tensor category where you have which is abelian, where you have notion of reducible models and kind of you can talk about Jordan-Gölder series, this number is defined, and you can well, you can try to compute it. So we have a conjecture that this number is going to be additive and additive in strong sense, in stronger sense than before. So if you have short exact sequence, so 0 to A to B to C to 0, then alpha of B is going to be alpha of A plus alpha of C. So this is short exact sequence. In particular, it's additive for direct sums, but this is kind of much stronger property. It's also, well, hopefully is multiplicative. And, well, maybe I should say that this is true whenever it's defined. So whenever defined. And defined means that this limit really exists, and this means that this an it should be bounded by some geometric progression. So kind of the only reason why this limit might fail to exist if this limit happens to be infinity. So if my an is bounded by some geometric progression, some constant multiplied by some maybe huge number power n, you can show that this limit really exists by the same kind of arguments as before. Well, so hopefully this number is going to play a role of Frobenius-Perron dimension for categories which are not finite. So kind of sums that is easy to show. So maybe this is exercise. So if my tensor category C happens to be finite tensor category, or maybe more generally, C has finitely many simple objects, but possibly not finitely many irreducibles. Then this alpha of V is going to be exactly Frobenius-Perron dimension of V. So if my category is finite, then it's Frobenius-Perron dimension, but this kind of allows you to define Frobenius-Perron dimension even for categories which are not finite. And Frobenius-Perron dimension, well, seems to be very useful and convenient too, and we really want to have some generalization of it. Okay, so I'm going to stop very soon, but I forgot to mention one very important thing about our theorem. So this theorem which tells you how this number beta of v is computed for representations of groups. So this is not expected to be true for, I mean, you can try to play the same game for representations of Hopf algebra, so something like this. So kind of, it turns out that this is not true for Hopf algebras. So for Hopf algebras, you can come up with examples. Well, this number beta of v is still defined, but it's not dimension of v. You can come up even with braided examples. Okay, so that's something to keep in mind. So kind of for this story, it's really important that categories that I have in mind are symmetric tensor categories. And I think that's all I wanted to say. So I hope there are some questions. Thank you very much.
Thanks, Victor, for the great talk. Let me stop the recording.